So in most collisions, some of the kinetic energy is lost or is transferred in the form of heat, sound, or is used to damage or change the shape of the bodies which are involved. So perfect elastic collision are very rare. Almost collision makes some noise, but hard object like a pool ball uh, will have a closer having elastic means closer to having elastic collision than a soft object, because soft object can collide and energy is used to deform the objects. So just copy the define elastic and inelastic collision and copy the last part. If a collision is an elastic collision, so if you have two objects of mass m1 and m2 moving with velocity u1 and u2, so the kinetic energy will be m1, because kinetic energy is half mv square. So it is half, or I can say 0.5 m1 u1 square, and kinetic energy of this one is half m2 u2 square. So total kinetic energy of objects before they collide is equals to total kinetic energy after the collision. So m1, this one is v1, this final one is v2. So it will be half m1 v1 square and half m2 v2 square. So when we compare these two equations, we can say half I will write as 0.5, so 0.5 mv square, m1 u1 square so 0.5 m1 u1 square plus 0.5 or half m2 u2 square is equals to 0.5 m1 b1 square plus 0.5 m2 v2 square. 0.5 is common, I can cancel out that. So I can say m1 u1 square plus m2 u2 square is equals to m1 v1 square plus m2 v2 square. Now, if two identical objects are there, if two objects have the same mass, if m1 is equals to m2, if in this equation mass 1 and mass 2 are same, so if I take m common, I can cancel out all the masses. So we can say u1 square plus u2 square is equals to v1 square plus v2 square, because m is common. And if initial velocity of first object is 0, means there was a stationary object collide with a moving object. So if one of them is 0, either u1 is 0 or u2 is 0. So I can say u1 square is equals to v1 square plus v2 square. Now this formula is important. You can see here, this formula is same like a Pythagoras theorem, in which we say hypotenuse square is equals to base square plus perpendicular square. So what does it mean? It means when two objects are colliding with each other, if object 1 collide with object 2, object 2 is stationary at rest, and object 1 was moving with the velocity u1. So when they collide with each other, what we will observe? We'll observe that the angle between them will be 90 when they collide if the collision is elastic collision. Is it clear? Means this formula is just to indicate or identify, because when we say if a collision is elastic, it means the kinetic energy before is equals to kinetic energy after. So we can say m1 u1 square plus m2 u2 square is equals to m1 v1 square plus m2 v2 square. If mass of objects are identical, so mass will cancel out each other. So we are left with u1 square plus u2 square equal v1 square plus v2 square. If original one of the object initially was stationary, then that formula turned into like u1 square is equals to v1 square plus v2 square. So it resembles with the Pythagoras theorem. So it shows that if two objects collide with each other, initially one of them is stationary, another one is moving, and it is at rest, one of this rest and another one is moving, and both objects have the same mass, then if the collision is elastic, the angle between them will be 90 degrees. Is it clear?
Yes, sir.
Okay.
So copy this for elastic collision. Write a heading like elastic collision for two identical objects if initially one is stationary.
Sir, could you define the statement, the 90-degree angle statement?
Yeah, if the two objects, sometimes they ask how you can identify that the collision is elastic between the two identical objects if one is stationary. So this resembles the final statement resemble with the Pythagoras theorem that hypotenuse square is equals to base square plus perpendicular square. So which shows that the angle should be 90 if the collision is elastic. Like the final statement, you will mention resemble with the Pythagoras theorem. So if final statement resemble with the Pythagoras theorem, so it shows that the angle between the two objects should be 90 for a collision to be elastic. In this question, a trolley of mass 2 kg at a speed of 3 meter per second catch up and collide with another trolley of mass 1 kg moving with 1 meter per second, which is traveling in the same direction. Following the collision, the first trolley has a velocity of 5 by 3 meter per second, so that the collision is perfectly elastic. Before showing that collision is perfectly elastic, what we have to do, we have to find the final velocity. How to find the final velocity? Because the momentum should be conserved. So m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. So first mass is 2 kg and it's moving with the velocity 3. The second mass is 1 kilogram, and it is moving with velocity 1 in the same direction. The first mass is 2. Following that, the collision of first trolley is 5, speed is 5/3, and the second one speed is v. So when we solve, you can see here it's 11/3 after solution. Now to show that momentum is perfectly elastic, so the total momentum, the total kinetic energy, to show that there's an elastic collision, the total kinetic energy of two objects, the sum of the kinetic energy of two objects before collision is equals to sum of kinetic energy after collision. So half mv square and half mv square, it's giving 9.5. Then half mv square plus half mv square, it gives 9.5 as well. So kinetic before and after is same. It shows that the collision is perfectly elastic. This is momentum in one dimension, but there is also momentum in two dimensions. So momentum in two dimension, because sometimes what happens, the object does not move in a straight line, does not continue to move in a straight line. It changes the direction. Say an object like in a billiard or a pool. So when it hits, maybe the blue ball here recoil, move in direction making certain angle, as well as the red also will move in certain direction. So if I say this velocity, this mass is m1, this mass is m1, it was moving with velocity u1. This mass is m2, it was initially stationary. When it recoiled, this is it's not recoil. When it changes the direction, this one is v2 and this one is v1. This is making angle theta, and this one is making angle phi. So in this case, actually the momentum is having two components, horizontal and vertical. So when the momentum is having the component such as horizontal and vertical, so we have to divide this conservation into two parts. Conservation of momentum in x component and conservation in y. So conservation in x. So basically this velocity will also have two components. The one which is with an angle, it will be v2 cos theta, and against the angle, it will be v2 sin theta. Same way, with an angle, it will be v1 cos phi, and against the angle, it will be v1 sin phi. So this we resolve the velocity into component. We resolve the velocity into vertical and horizontal component. So when we check the conservation in x direction, so first initial momentum, this object was moving horizontally, so its momentum is m1 u1, plus the second object was stationary. So if it is stationary, its momentum will be 0, equal. So the second momentum of object 2 means momentum after collision for object 2 and object 1, they have component. They have horizontal and vertical component. So the horizontal component of a momentum for first object, it will be m1 v1 cos theta plus m2 v2 cos phi. So m1 u1 is equals to m1 v1 cos theta plus m2 v2 cos phi. Because it's in x direction, these are the components in x direction. And then what about the component in y direction? Because initially m1 and m2 are not moving in y direction, so y direction there is no momentum. Then for m1, the direction is m1 v1 sine phi. This is, if one is down, another one is up. So if one I take as negative, the other one should be positive. So if I take this as negative, the other one will be positive. So it will be m2 v2 sine theta. So is it clear? So basically what we did, when the momentum, the motion is having two components, horizontal and vertical, so we'll divide it and separately we'll solve the horizontal and vertical components. This is it clear? How we separate the momentum into two parts?
Yes, sir.
So copy this conservation of momentum in 2 dimensions. Then the relation between the momentum and kinetic energy for non-relativistic particle. What is the term non-relativistic? When the particles are not moving close to speed of a light, we call that as non-relativistic particle. If a particle moves close to speed of a light, actually the mass of the particle does not remain same. The mass increases as the particle or an object moves close to speed of light. We call that as relativistic effect. So for a non-relativistic particle, the particles which are not moving close to speed of a light, we can have this relation. As we know, the kinetic energy is half mv square. So what we can do, we can substitute the kinetic energy is 0.5 mv square or half mv square. So if I multiply and divide this equation by m, I multiplied by m also and divided by m. So this will become kinetic energy is equals to m multiplied by m is m square and v square divided by m. Then kinetic energy is equals to half m multiplied by m, actually m square v square. So in a bracket I can put m into v whole square divided by m. And mv is actually momentum p. So I can say kinetic energy is equals to momentum square divided by 2m. So what it shows that momentum and kinetic energy, what is the relation between them? So kinetic energy is directly proportional to momentum square. Means if we double the momentum, the kinetic energy will increase by 4. If we triple the momentum, if momentum is multiplied by 3, the kinetic energy will increase by factor 9. So the graph between the momentum and kinetic energy, if momentum is on x-axis and the kinetic energy on y-axis, so it will be a curve which gets steeper as we increase the momentum. Is it clear?
Yes.
So basically apply the principle of conservation of energy So if there is no external force, the momentum is always conserved. However, the kinetic energy is not always conserved. If the kinetic energy is conserved, we call elastic collision. If it is not conserved, then we call that as inelastic collision. Uh, so here, this is a graph for force and time graph during a collision. For example, the diagram below shows a possible graph force against a time during a collision, means when objects are colliding. For example, a ball is hitting the wall. So this is a ball and the ball is moving towards and it is hitting it. So before and after collision, there is no horizontal force on the ball. The total change in momentum in its initial collision with the wall is given by area under the graph. Because if we need a change in momentum or impulse, I told you force and time graph, if we calculate the area under this graph, like this whole area, that will give us the impulse. So first what happened? The ball, as it hits the ball increased, like it deformed at point 1. This is a point where the ball just come in contact. This is just an explanation how the conservation of momentum is there and how the momentum changes. So as the ball hits, this is a point where the ball hits. Then point 2, what it shows, the ball increasingly deforming squashes due to the force exerted by the ball. So as the ball hit the wall will exert force on the ball, so it will squash this or deform the ball. Then the ball reverses direction or changes the direction, and then ball start to return to its normal shape, and then the ball loses the contact with the wall and the ball will move away. So the exact shape of the graph would depend on the material of a ball which it is made up of. For example, if the ball was very hard, then it would not deform significantly during a collision, and the spike on the graph would be much narrower. Means this part will be narrower, showing that the collision is in much shorter time, and very squashy ball deform readily leads to flatten the graph. Means if a ball is, like example, made up of a rubber or any object like same like a sponge, so then what will happen, the graph will have a greater, or it will have a flatter graph will be there, and it will collision last for a longer time. Is it clear? This force time graph for a collision between the ball and the wall.
Yeah.
So next class I will continue this momentum and we'll do some questions related to. You don't have to copy this. It's just an explanation of. So next class we'll also continue momentum and we'll do questions from the past paper related to topic momentum.